So now we're going to talk about 3 different types of chemical reactions. The first one's combustion. Combustion is burning. What's required for something to burn? Oxygen. You might think, well, air. Yeah, it's the oxygen in the air that we need to combust, to burn something. So combustion is a reaction of oxygen, and in that reaction, the oxygen gets combined with something, so we get an oxygen-containing compound, and we also get heat. And we should be able to remember that, because when you burn something, it's hot, right? So we're going to learn about compounds containing carbon, hydrogen, and oxygen only, and how those burn. And the products are always carbon dioxide and water. So you just remember it. If the reactant is carbon and hydrogen, or carbon, hydrogen, and oxygen, you're burning it, you're going to make CO2 and water, because I said so. So as an example here, natural gas, CH4, combines with oxygen, produces CO2 and water. So let's write a balanced equation for the complete combustion of liquid C2H5OH. It's ethanol. So this is the sort of thing that you could be expected to do on the next exam. Okay, so we give you the formula for that reactant, C2H5OH, and we tell you it's a liquid. And that's it. Complete combustion. What's required for combustion? Oxygen. So my other reactant is oxygen. And because oxygen is a diatomic element, it's O2. And I think we're all aware that oxygen is a gas at room temperature. And so then I've got my arrow, and what are my products? CO2 and H2O. Why? Because I said so. Now, what's the state of water here? It's probably going to be a gas, because a combustion reaction is going to be hot, right? So you go home and turn on the gas stove. Do you see water coming out of that? No. But if you hold something that's cool above it, you'll get condensation on that object. And that's from the water vapor that's the product of the combustion. So there's our reactants and our products. We need to balance this. Let's just try balancing by inspection, start with the carbon and just move through and see how that works. How many carbons on the left side of the equation? 2. So that means I need 2 on the right side. So if I put a 2 in front of CO2, then I'll have 2 C's, right? Next, I'm going to do hydrogen. This is H5, and there's another H here. It's written this way because the chemist then recognizes this is an alcohol. So I've got 5 and 1, a total of 6, and no hydrogens there, so I need 6 hydrogens from my water. So I'll multiply by 3. Yeah? And now I've got oxygen saved for last. I've got the oxygen here, and I've got 1 oxygen over there. And so let's count up what I've got on this side. I've got 2 times 2 and 3 times 1, right? So 4 plus 3, 7. And over here, I've got 2 and 1. I need this to be 7. So what do I need to multiply that by? 3. If I put a 3 in here, 3 times 2 is 6, 6 plus 1 is 7. So I didn't need to double everything on this one. Questions? So there are a lot of other combustion reactions. Hydrocarbons are not the only thing that can burn. Metals can even burn. But this is the only kind of combustion reaction that you need to be able to write equations for. The other reactant is O2. The products are always CO2 and water. Now this says complete combustion. What happens with combustion if there's not enough oxygen, like the vent to the gas heater is blocked and so it doesn't get enough oxygen, it'll still burn, but you'll get carbon monoxide instead of carbon dioxide, and then that fills up your home and kills you in your sleep. Very tragic. Okay, alkali metals, very, very reactive, not found in nature as uncombined elements. They react very vigorously with nonmetals. So we're going to learn about their reaction with halogens. So alkali metals, and here we're using an M just to stand in for any of the alkali metals, could be lithium, potassium, whatever. And the halogens, and we're using X to represent a halogen, those are fluorine, chlorine, bromine, iodine. So those would react according to this pattern. So here's a specific example, sodium and chlorine. Here's the sodium, 2M, 2 sodiums, and the X2 here at Cl, Cl2, all of those halogens are diatomic. They react to form sodium chloride. We can predict the products. We know it's always going to be Mx because these alkali metals always form +1 ions. The halogens always form -1 ions. So it's going to be one of each. As you go down from lithium, sodium, potassium, they get more and more reactive. So this looks like a pretty vigorous chemical reaction. So the reaction of rubidium with chlorine is going to be even more vigorous. Probably pretty dangerous. Alkali metals also react with water. Here we have photographs. Here's lithium reacting with water. It kind of fizzes and zips around. Here's sodium reacting with water, and we've got a little bit of a flame going on here. And here's potassium, more of a flame, and then there's like sparks flying all over the place. So what happens here is the alkali metal reacts with water. It forms metal ions, hydroxide ions, and hydrogen gas. It's also exothermic. It releases a lot of energy, and it's usually enough energy to spontaneously ignite the hydrogen. And so that's why they're pretty explosive. You can find YouTube videos where people throw chunks of sodium in their swimming pools. Like, I wouldn't do that to my own swimming pool. Maybe somebody else's swimming pool, but not mine. Stuff like that's dangerous, right? If you don't know what you're doing, you can get hurt. It's fun to watch other people do it. The halogens. The halogens are very reactive nonmetals. Here we have pictures of them. Chlorine is a gas at room temperature. Iodine is a solid at room temperature, but it sublimes quite easily and forms this purple gas. We're actually going to use solid iodine today in our experiment. And then here's bromine. Bromine is the only nonmetal that's a liquid at room temperature. But it evaporates quite easily and gives you this brown gas. Yes?
Subliming is solid to gas?
Yes, subliming is solid to gas. And if you ask me, because I'll forget otherwise, I'll show you iodine subliming. This is really fun and messy. So we can get a reaction between metals, not necessarily an alkali metal, but any metal can react with a halogen. It'll form a metal halide. So instead of chlorine, or chloride, we're saying halide. We take the name of the family and make it into an ion name. The numbers here are going to depend on the charge of the metal ion, right? So if it reacts with aluminum, we know aluminum makes a +3 ion, and so then this is going to be MX3 because it would take 3 chlorides. They can also react with hydrogen to form hydrogen halides. These look like acids, right? These are gases at room temperature, but if they're dissolved in water, then they're acids. And they can also react with each other to form interhalogen compounds, like PCl3 and various things like that. Okay, so we should be able to do some things like this. The one in the middle is kind of challenging, but we're going to do it anyway. So writing some chemical reactions, chemical equations. So the reaction between aluminum metal and chlorine gas. Well, start by writing the formulas for the reactants. We've got aluminum metal, solid, and chlorine gas, Cl2 gas. And then how are those going to combine? Well, we actually learned how to figure out the formula for this product back in chapter 3. What ion does aluminum form? 3+, because it's in group 3. And what ion does chloride form? -1. So I can predict the formula of the compound by the charges. So this is going to make AlCl3. Now what's the state of that? What's an ionic compound that you're familiar with? You probably put some on your eggs this morning. Salt, right? What state is salt at room temperature? Solid. If you put some salt on the stove and heat it up, does it melt? No. You can melt it, but probably not on your kitchen stove. Much, much higher temperatures. So pretty much any ionic compound is going to be a solid at room temperature. I would not try to trick you with that one. Yeah.
Since it's Cl2, would that change the charge to this 2?
That's a good question. Since this is Cl2, does that change the charge of this? No, it doesn't. So this chlorine molecule of 2 atoms will separate into the individual atoms. They'll each gain an extra electron, and you'll have 2 chloride ions. Yeah. We'll talk more about exactly how that happens later, but we're just going to use these same predictable charges from the periodic table. So chlorine always forms Cl-. Doesn't matter what it's coming out of, it's just Cl-. So then we need to balance the chemical equation. I have 1 aluminum and 1 aluminum, 3 chlorines and 2 chlorines. What do I do? What's the least common multiple of 2 and 3? 6, right? So if I put a 2 in front of the product, I'll get 6 chlorines. And then if I put a 3 in front of my Cl2, I'll get 6 chlorines. And then I have to go fix up the aluminums, and that'll get a 2. So practice balancing equations. The reaction between lithium metal and liquid water. This one's a little more challenging because you actually have to remember a fact or remember a concept. This one you could kind of figure out just by saying, well, what kind of a compound would these make, and then balancing the thing. You don't really have to know any extra stuff. You just have to be willing to go at the problem. So when alkali metals react with water, explosions happen, very violent. And the explosive part is because of the hydrogen gas. So hydrogen gas is formed, and I would expect that most of you would not remember that. It's okay. And then it makes an ionic compound. So the lithium becomes an ion, and the other ion is going to be hydroxide ion. And again, that's going to be kind of hard to remember. So how do I balance this? Well, everything's fine except the hydrogens, right? I've got 1 lithium on each side, and I've got 1 oxygen on each side. But hydrogens, I've got 3 on one side and 2 on the other. This might be a situation where you'd want to use a fraction initially. Here I have hydrogen all by itself. I can change this one without messing up the others. Lithium and oxygen are already balanced. if I go changing this one or this one, then I'm going to mess those up. So if I made this different, I could balance it, but I need less, right? I could put a 1/2. If I had half a molecule, which isn't possible, but if I had half a molecule, then it would balance, right? Move your head like this. Question? No? I'm not done because we can't have fractions in our balanced chemical equation. So what I need to do then is multiply everything by 2. So 2 lithiums, 2 waters. I multiply 1/2 by 2 and I get 1. And 2 lithium ions and 2 hydroxide ions. There's a couple of ways you could come at that, but that's the one correct answer. Yeah?
I got lithium with 2 waters and 2 hydroxides, but not balanced out.
Well, you have to have the hydrogen in there. Hydrogen
I mean,
gas.
it makes 4 hydrogen on each side.
Yeah, so here I've got 2 hydrogens and 2 hydrogens and 4 hydrogens. But if you just have if you had 4 hydroxides, you're going to have too many oxygens.
You know, 2 on each side?
Well, I've got 2 on each side.
Well, I'm just asking, why would you double the lithium?
Oh, that's a good question. I see what you're asking. So that's an excellent question. The answer is balancing redox reactions. The answer to that is beyond what we've talked about so far. If I have 2 lithiums here, then the total charge over here is +2 and -2. The total charge here is 0, and the total charge there is 0. If I get rid of this 2, which I think is actually how I balanced it yesterday. I think I balanced it like that yesterday. Now, the atoms are right, but I seem to have gained an electron somewhere. Yeah. Thank you for pointing that out. So I was going with the way the book shows they show you doing the ions separately. So if we say it's lithium hydroxide, aqueous, putting the 2 together, now we're going to get the lithiums correct because we need 2 of these with 2 of those. But what the book showed us over here, they showed the individual ions. So I was trying to go with that, and now I'm like really wishing I hadn't. But thank you. So that one, I would consider that a mean exam question. That'd just be mean. So I'm probably not going to give you that on an exam, but it could be in homework or something. Reaction between gaseous hydrogen and liquid bromine. This one's easier. Well, what's the formula for hydrogen? H2. It's a gas. This is where we need to know our 7 diatomic elements. Right? Horses need oats for clear brown eyes. H for horses. And liquid bromine. That's Br. Is it diatomic? Yeah, that's the brown. So Br2, and they're telling us it's a liquid. We can also see that it's a liquid from its color on the wall periodic table. It's blue. That means it's a liquid at room temperature. And these are going to react. Well, we're going to have hydrogen and bromine together somehow, right? So H and Br, and then the question is, well, is it H2Br? Is it HBr2? How do we put them together? Does that look a little bit like an acid? Yeah. This is an acid if it's dissolved in water. So if I dissolved it in water, I would get hydrogen ions and bromide ions. +1 and -1. So that's what tells me that I need one of each. This would be in the gas state. I wouldn't expect you to remember that. But this would be a gas. But that would be the formula. And then how do we balance the equation? Put a 2 in front of it. Yeah.
How do you know it reacts with water? Is it just because you know it's an acid?
This one or this one?
Both.
C? Well, it's not reacting with water in this example. But when I see a compound that starts with H, I think acid. But technically it's only an acid if it's dissolved in water.
Also, just assume that in order for it to be an acid, it has to be dissolved.
Yeah, an acid has to be, the definition of an acid that we're working with is when dissolved in water, it produces hydrogen ions. So I'm seeing H and something else, I'm thinking this looks like an acid, so I'm thinking, well, if it was acting as an acid, then it would make ions, and I can use those ions to predict how it's going to go together. Without charges, H and Br, how do you know how many of each? You kind of don't.
So say it was saying like reaction between hydrogen, a gas has hydrogen and but if it said it was reacting with sulfur, you can assume the same thing.
Yeah, I would expect you to assume the same thing. So let's say we're doing hydrogen and sulfur and just the monatomic form of sulfur. How are those going to go together? Well, you're like H and S, so that's looking like maybe a hydrosulfuric acid or something. So what's the charge on the sulfur ion? -2. So if this is 2-, then I need 2 H's. It would be H2S. So A and C, I think, are reasonable questions. B is a bit much. Any questions?